Okay, welcome back. Now I will discuss about the second lecture of Module 2, which is image classification pipeline. I will discuss about the high-level concepts, early stage achievements regarding image classification. As you remember, we have discussed about visual recognition from the perspective of image classification in our previous lecture. Now I will dive a little bit more on image classification aspects, starting from the earliest approach like nearest neighbor, k-nearest neighbor, and I will conclude this chapter by or session by discussing about the need for non-linear classification mechanisms rather than linear mechanisms. Okay, so image classification is a core task in computer vision. It's like assume we have this kind of real-time entity. It could be dog, cat, or some other thing, and you will be asked to classify or to label or to categorize the features, the characteristics. It could be visual or other types of features into a predefined set of classes or categories. Okay, so image classification basically it's all about classifying a real-world entity or a combination of them into a noun set of categories. Okay, a noun set of categories. So you could have, for instance, for this type of inputs, you may have labels like possible labels like dog, cat, truck, plane, and the image classifier as a model, whether it is linear or non-linear, is supposed to generate a label that describes the features, the most dominant feature in the given image or in general data. So basically, image classification is the most important task or a core task in computer vision. But it comes along with different complications and problems. The first problem here is the semantic gap. By semantic gap, we mean the difference between how we perceive real-world entities and how computer sees them or how computer perceives them. For instance, as we already discussed in the previous module, we know computer perceives image, for instance, 2D image as a matrix, as a 2D matrix, right? So image is just a big grid of numbers, and specifically for RGB image with 3 channels, it's like a grid of numbers between 0 and 255, describing the degree of pixel intensities for each pixel. So assume, for instance, you have an 800 by 600 image of cat with 3 channels, each channel belonging to red, green, and blue respectively. Then the computer basically understands this image as an 800 by 600 uh, uh, 2D matrix in 3 different perspectives or channels. So the problem with image classification generally comes along with how computer perceives image or the real world, which is as um, a multi-dimensional matrix. Okay, so that's a big difference between how we perceive and how computer perceives. Like this is major the source of every problem that we are going to talk about in the next few slides. But and also this brings us another challenge, which is called viewpoint variation. Um, for instance, assume the camera moves. So for the same object, okay, for the same object, the viewpoint that you are at time t might yield some, two-dimensional matrix of the image that you are targeting. And if the camera moves, or even if you move as a camera, assuming yourself as a camera, then the pixel intensity variations, combinations that you see for the same image will be different. So this is one of the most important challenges in computer vision in image classification. We categorize or we label this problem set as viewpoint variation. So just having the same target image, uh, if you change your like orientation, for instance, against that image, then the combination of pixels or the data, the matrix data will change significantly. So this is a major issue. The other challenge is illumination. The same object might have different pixel intensities in different color or in different light scenarios. So this is, again, this has been a major problem in digital image processing, as you remember. Whenever the lighting conditions differ or the illumination differ, then the histogram obviously will differ, and that will cause us to do some more tasks to identify or to label two different the same image with two different illumination, okay, as one image. So that's a common problem in computer vision, which is illumination. The first one is viewpoint variation. Even in digital image processing, viewpoint variation is the most common problem. For instance, there is this uh, problem called camera jittering, right? So camera jittering is basically the problem that you face when you see the same image using a moving camera. Okay. Um, so that's one, viewpoint variation. The second one is illumination, as I already discussed. The third one is deformation. The same image might have, or the same entity, the same foreground image, might have different shape at different time. Okay, so you should be able to even recognize the different possible formations of the same object. Okay, so it might deform from time to time, or the same object might be in different shapes. So that's one of the characteristics of real-world entities, and computer vision should be able to identify that one. Occlusion, which is the property of partially covered foreground objects. So we discussed about occlusion in our previous chapters as a benefit to some extent, but here again there are also challenges because it's easier to identify objects which are not covered than objects which are partially covered by other foreground objects. Okay, so the degree of complexity of image classification increases as the degree of occlusion increases for any type of foreground image. Similarity between foreground image and background image is also one of the most challenging things in computer vision, which we call it background clutter. So, for instance, if you see this image to the right of the screen, there is, I think, something which looks like snow in the background, right? So, and again, the image, the foreground image, the cat, has similar features as the background, which is like cloudy white. The same is true for the leftmost image. So this problem, in general, we call it background clutter. So these are, the challenges that we face while dealing with computer vision or specifically image classification. The other one is interclass variation. Intraclass variation is a variation within a class. For instance, all these foreground objects could be categorized or labeled as cat, but there could be other intraclass classification need. For instance, classifying the cats as wild cats, like homey cats or something like that one. Okay, so this is another challenge which has some semantic aspects in addition to structural or syntactical aspects. So when we get back to image classification, so the image classifier could be considered as a function, a simple function, okay, that takes image as an input and returns class label as an output after performing some magic, okay, quote unquote some magic. So it's not like sorting a list of numbers or computing addition between two numbers or a set of numbers, because we cannot hardcode this one. We cannot hardcode the classification of a foreground object as, cat or dog or deer or lion. It's not possible to hardcode it. So that's why I said there is some magic in between accepting images and generating class labels or classifying that accepted image. So one thing, it cannot be hard coded. Okay, it cannot be hard coded. So there should be some kind of mechanism to transform the image into label without hard coding it. Okay, with the capability to generalize on unseen circumstances. I'll discuss about that one in detail in the next few slides. So just assume image classifier as a function for now, a function that takes image as an input and returns class label. Since we are talking about classification, we're going to base our operation on a destination called class. So uh, there could be only two classes in case of binary classification, for instance. Something could be cat or some other thing, or there could also be multi-class classification in which there will be more than two classes like cat, dog, hyena, lion, something like that one. So there has been multiple attempts made to come up with a hard-coded approach to identify objects or to classify objects. For instance, we have been doing this one. Probably you have done this thing in your Module 1 project. We have also been doing this in the Module 1 lecture series. We have been discussing about edge detection techniques, different mechanisms for segmentation and various computer vision or digital image processing techniques. So there have been attempts to classify foreground objects based on hard-coded methodologies. We will not belittle this one. We are not belittling those approaches. Those approaches could work in some contexts and scenarios, but since we have discussed about the limitations of such kind of approach in our previous lectures, we need some better approach to classify objects without hard coding. So in the previous approach, for instance, there is this input image. So we might find edges and come up with this binary image. And from that binary image, we might apply some hard-coded functions, like a function to find corners, okay? To find corners based on these directions. And based on the nature of, or the set of corners that you have identified from the image, then you can say this is human, this is female, this is male, something like that. But it's not that realistic. But for some, objects that can be identified or classified from shape mainly, rather than appearance, this kind of approach could work. Okay, obviously they work to some extent. But the state of the art in this regard, data-driven approach rather than hard-coded approach. So in case of data-driven approach, the first step is to collect a data set of images and their corresponding labels. That means you might have a set of images of airplane and you have to label them as airplane. And the same will be true for all other classes that you are going to define. Then the second step would be to train a machine learning model as a classifier model. And the third one is to evaluate, to iteratively evaluate your classifier model on newer image. So here we can define again this classification problem in two perspectives, from two compartments. The first one, training phase, and the second one, prediction phase. Okay, it's very high level definition of data-driven image classification. So in the training phase, the trainer function accepts images and their corresponding labels, and they try to fit images to their corresponding levels. We call it training in general. Then once we get what we expected from the training phase, then it will return some model, which is a set of weights corresponding to relations between images and their corresponding levels. And once we have this model, then we will use this model to predict the labels of new image. We call this image test image. So for that, we need predict function. Okay, by the way, just practically when we work on this type of things in the lab or while doing in the development environment, we might not use only two functions. We will not use two functions usually, just for ease of academy or for ease of pedagogy. I'm discussing this one as a two-compartment problem, okay? But it could be, for instance, a combination of train class and predict class. It could even be, a set of train package and predict package, okay? As the problem grows, then your organization, your modules organization also grows, and its sophistication will also grow. So the first one is training, the second one is prediction, okay? As I already mentioned, the training phase takes images and their corresponding levels and yields model. the prediction phase takes the already built model, which is a set of weights characterizing the nature of data, the data that you feed, and the you know when it comes to the second one, prediction phase, we have two things: the model one, which is as I already said, set of weights, and test image, which are unseen image or unseen world. This data set in the next consecutive chapters. So again, from what we have been discussing about so far, we can, you know, uh, define nearest neighbor algorithms in the based on by using the image to the rightmost side. So here we have, for instance, test image and nearest neighbors. Okay, here we have one image and its nearest neighbor here to the right side. So just generally, we can define nearest neighbor as a classification technique that labels new image based on its similarity with the existing image. Okay, its similarity with the existing image. So what are the metrics we could use for nearest neighbor? We could mention two types of metrics. For instance, L1 distance. Usually L1 distance is Manhattan distance, could be used. So here, for instance, the sum of the absolute value of difference between two pixels for each pixel in the test image and training image is taken to calculate the distance between two images. So the gamma tailed D1 of I1 and I2 ማለት distance 1 between image 1 and image 2, okay, I የሚለውን በፒክስል ደረጃ የምናየው እንችላለን, is the sum of the absolute difference of each pixels from the test image side to each corresponding pixel to the training image side. So here assume this is a 4x4 image of test image, and again here we have a 4x4 training image. So basically L1 distance or Manhattan distance calculates the difference between the corresponding pixels, the absolute difference between corresponding pixels, and sums up all these pixel differences to get the D1 or the L1 distance, which is calculated as 456 in this scenario. So L1 distance could be used to lead nearest neighbor choose the best training image for the new test image. That's one. The second one could be L2 distance, which is Euclidean distance. You can also use Euclidean distance, which is square root of the square difference of these two I1 and I2. Okay, the sum of the square difference of I1 and I2, that could also be used. In the previous class, that means not in this computer vision class, but in the previous course, which is in AI principles and techniques, we discussed about Manhattan distance and Euclidean distance while dealing with informal search, I guess, informal search. So it's better to recall those concepts. So we will be using Python. We will be using Python, OpenCV, NumPy, SciPy, different Matplotlib, different libraries which are important for machine learning from the Python perspective. So for instance, by using Python, we can model the nearest neighbor algorithm as follows. If you haven't, I think you are second year students, I guess, now, so you should be able to write a very good Python code and also understand any type of Python scripts. So for that, I will not recommend you to reread about Python, especially object-oriented Python. But if you have some gap regarding Python, I recommend you to but to read some of the manuals that I have published, for my previous students. Okay, if you want, I can also republish them to your channel, and then you can practice using them. But for NumPy library, I have added a tutorial which is recommended by Stanford University. It's better for you to check that tutorial. Okay. So here, for instance, in the case of nearest neighbor, we have a constructor which doesn't have anything, which that means nearest neighbor is considered as a class which doesn't have any state. Okay. We have here a train function which takes x, which is input, and corresponding label y, small y. Okay. So here we assign the accepted input and corresponding labels to the object or instance type variables xtr and ytr, which corresponds to input data and the corresponding level respectively. We have another function which is a high level function again, predict, that takes that initializes first an emp test to hold a set of just a set of labels, which is defined by the shape of x, and we have also ypred, which lets the function store the predicted labels in a way that is that matches the input type. So here we have iteration. In this iteration, we try to calculate. Sorry. So in this iteration, we try to calculate the distance between the new image, the new image, and each of the other images in your dataset. So that's just each of the other images in your dataset. The nearest neighbor will have track of all of those images, XCRs, or input image or training image, so that it can compare the difference between the new image and all those training images at this phase. This is the phase it might require. It require the all the labels and training image for calculating distances. So from that, it takes the image with minimum distance. Among those all images, the image with minimum distance will be taken using this one, and the index of that one will be taken as mean index, because as I already mentioned, theoretically, the nearest neighbor takes or computes the distance between the new image and all other images in the training set, and it takes the image that has smallest distance with the new image, right? So for that purpose, we have to take the index, assuming the images are listed as a set, as a list. Okay, we have to get the index of the image with the minimum distance compared to the new image as mean index, and using that we set the predict value at that point I by using the minimum index or the label of the image which is identified by the mean index here in this phase. So it's pretty simple implementation of nearest neighbor. Most of the things are high level here, but it's implementable, easily implementable. So here we said it memorizes training data. Nearest neighbor memorizes training data. Here you can see it accepts all training data and your training image and labels, and it assigns it to the corresponding instance variables for both training input for training image and label, corresponding label. The other thing, for each test image, it finds the closest train image and then predict label of nearest image. That's shown here in the for loop or looping loop statement. Okay. So as you can see here, for each new image in this set, the nearest neighbor usually computes for that means calculates the distance between that new image and all other images. So assuming, for instance, the number of images in the training set are n, okay, and assume for the number of images in the test set are m, then for each of elements of m, then n times computation will be done. So usually for each of test image, we'll have O of what? O of n complexity. I'm sorry, I'm slow while writing this one. So O of n ይኖረናል ማለት ነው. So this is very expensive አይደል? So ለሙሉ ኢሜጅ ስንሄድ m times n አይነት ነው የሚኖረን. So assuming m is equal to n, for instance, if you have the number of test images which are equivalent to the training image, then the complexity will be n raised to 2, right? N raised to 2, which is m times n. But for general cases, it's m times n, whether m is equal to n or m is not equal to n. So nearest neighbor, from what we discovered so far, is a very expensive classifier. Even though it's simple, it's expensive. So for training, you might take O of 1, but for prediction, for each of O of 1, you take O of n. So this is very bad, and we want classifiers that are fast at prediction and could be slow for training. Okay. So, for instance, from this image, how do you classify things? For instance, what does this look like? What kind of nature does it have? How can you label each of these features? Okay. So from that perspective, for instance, for such kind of multivariate inputs and characteristics, you might enhance nearest neighbor algorithms to k-nearest neighbor algorithm. For that purpose, we enhance nearest neighbor algorithms by k-nearest neighbor algorithms. So k-nearest neighbor algorithm, rather than considering the best distance, we consider multiple classes, okay, and the majority, like for instance, we might take top 10 data items that are nearest to this element, the new image, and the majority class resembled by those 10 data items will be given to will be given as the label of the new image ማለት ነው። rather than አንድ ከሚሆን ይልቅ ለምሳሌ ከዚህ ጋር ቅርርብ አለው ከዚህ ጋር ቅርርብ አለው እንደምታዩት። ኦኬ ይሄ ትክክለኛ ቅርርቦች ናቸው እነዚህ እዚህ ጋር የምታያቸው። then የሁሉም ይሰራና ለምሳሌ ዘ ቶፕ 10 ሊሆን ይችላል። ለምሳሌ ኬያችን 10 ነው ብለን ብናስብ ከ10 ውስጥ ለምሳሌ በእኛ ኬዝ ለምሳሌ 9ኙ እዚህ ክላስ ውስጥ ነው የሚወድቁት፣ አንዱ ደግሞ እዚህ ክላስ ውስጥ ነው የሚወድቀው ብለን ብናስብ then በሜጆሪቲ ቮት k-nearest ምን ያደርጋል? ክላሲፊኬሽኑን ለዚህኛው ክላስ ይሰጣል ማለት ነው። ቤዚካሊ ልዩነቱ እሱ ነው። k-nearest neighbor እና ሌሎች ሌሎች ክላሲፊኬሽን ሌላው ክላሲፊኬሽን nearest neighbor የምንለው ክላሲፊኬሽን አንጻር ሶ ሜጆሪቲ ቮት ፕሪንሲፕል ያለበት ነው ብለናል። ኬ ቫሪ ያደርጋል። ለምሳሌ ኬ አንድ ሲሆን ቅድም ያየነው ኒረስት ኔበር ነው። ኦኬ ኬ እያደገ በሄደ ቁጥር ደግሞ መልቲፕል ክላሶችን ኮንሲደር ያደርጋል። ሜጆሪቲ ቮት ፕሪንሲፕልን አፕላይ ያደርጋል። ኬ ኒረስት ኔበር ኢትስ አጌን ኢሜጅ ክላሲፊኬሽን ቴክኒክ ነው፣ ግን ዳት መች ኮምፕሌክስ ለሆኑ ሲቹዌሽኖች ላንጠቀመው እንችላለን ማለት ነው። ቅድም ካየነው ኢሜጅ አንጻር ለምሳሌ ኬ ኒረስት ኔበር ለምሳሌ ይሄኛው ኒረስት ኔበሮቹ እኚህ ናቸው ብሎ ክላሲፋይ ሊያደርግልን ይችላል። ኦኬ ሶ ከነዚህ ውስጥ ካሉት ውስጥ ለምሳሌ እዚህ ጋር የሚታየኝ ወደ 10 ክላሶች ናቸው፣ 10 ኢሜጆች ናቸው የሚታዩኝ። ከ10ሩ ኢሜጆች ውስጥ ሜጆሪቲዎቹ የቱ ጋር ነው ያሉት የሚለው ይታይና ለዚህኛው ሌብል ይሰጠዋል ማለት ነው በኬ ኒረስት ጊዜ። ኦኬ ሶ በዚህ መልኩ የምታዩት ይሆናል ማለት ነው። እንግዲህ ቅድም ስናወራ ነበር ስለዚህ ኤል1 እና ኤል2 እያለን። ኤል1 ምንድነው ብለናል? ማንሃተን ዲስታንስ ነው። ኤል2 ደግሞ ዩክሊዲያን ዲስታንስ ነው። ሶ ኢትስ the square difference, square root of sum of square difference between two pixels or two images ነው ዩክሊዲያን ዲስታንስ። ይሄኛው ደግሞ the sum of the absolute difference between two images ነው ማለት ነው የማንሃተን ዲስታንስ። ሶ ኬ ኒረስት ኔበር ዲስታንስ ሜትሪክሱ እነዚህን ኤል1 እና ኤል2ን ሊጠቀም ይችላል ማለት ነው። ኦኬ ሶ በዚህ ኬዝ ለምሳሌ k is equal to 1 ብንወስድ then ኬ ኒረስት ኔበር የኒረስት ኔበርን ካራክተሪስቲክስ ነው ሪዘምብል የሚያደርገው፣ የተለየ ነገር ሪዘምብል አያደርግም። ሶ let's talk about hyperparameters from this simple classification algorithm perspective. ሶ እንደዚህ አይነት ቦታ ላይ ስንሄድ ኢሜጅ ክላሲፊኬሽኖችን በኬ ኒረስት ኔበር አይነት አልጎሪዝሞች ስንሰራ we have to tune or we have to set some hyperparameters, and the hyperparameters for k nearest one of it is, for instance, the classes, number of classes. So this hyperparameter tuning, like selecting the number of k's, the type of distance, is very problem dependent. So it's required to check them out and see which one works best in what condition. Okay, general idea while setting hyperparameters, the first idea is choosing hyperparameters that work best on the data. So you will have your data set, your own data set, then the hyperparameter, the number of k's, the distance type that works best on the data sets that you have at hand is the one to be chosen. So in case of, for instance, k is equal to 1, in case of uh, number of participants being 1, um, so this hyperparameter, any hyperparameter like works best. For instance, k is equal to 1 always works perfectly on training data, because in the training data we have all the information, and the one with the best distance with the new data is obviously going to resemble the class of the new data. Okay, so that's applicable. The second, so for that purpose, this cannot give us a model that can generalize on unseen environments. So for the training, it's best, the idea one is best for training, but not for general production purpose or environment. So the second idea comes, this idea, in this idea, we split data into train and test set, which is a very common approach while fitting models. And we choose hyperparameters that work best on test data rather than training data. Okay, so here we might not use k as 1. So our main target is about choosing hyperparameters that works best on the test data rather than the training data. So this is also bad. This is mainly due to the fact that we have no idea how the algorithm will perform on new data. Okay, on new data. So for that purpose, this is not usually recommended. The third idea would be to use additional compartment of data, which is called validation data. So in this way, we simply choose our hyperparameter on the validation data and evaluate the performance or the conduciveness of our hyperparameters on the test data. So it's two-phase um, validation technique. So this is the better approach. It's recommended most of the time. Even while building models for large-scale problems, we use these three compartments: train, validation, and test. Usually, we use for instance, 60% of training data, 10% of validation data, and 30% of test data. This is common division or classification among the data at hand. But you could also use other percentiles that's suitable for your problem domain. The other idea, again, sometimes it's not realistic for large scale data sets or larger data sets, but very ideal for building models which can generalize in in different environments, is cross validation. In case of cross validation, it's n-fold. Its other name is n-fold validation. That means it lets you split data into folds and try each fold as validation and average the results. Okay. For instance, here we have the whole data. Okay. Here we will have the whole data, and the whole data, as we already discussed, is divided into training and test. From the training data, we have, for instance, if the fold is, say, like 5-fold cross-validation technique, according to idea 4, then the fifth fold or any fold, any one fold from this 5 divisions or compartments will be used as a validation data, and the parameter which works best for each of these v-fold is taken, and it will be done for all consecutive folds. We have to change the target or the subject entity, which is subject for validation purpose in each of these iterations. And finally, we average results acquired from all these iterative processes. Okay, so as I already mentioned, it's useful for small data sets, but not used frequently in deep learning problems. Actually, I have used this one in my I guess third paper. I guess yeah, it's my third paper. So I used this one uh, mainly not during the first phase of my research, but after submitting it to one journal. The reviewer explicitly asked for n-fold cross-validation so that he makes sure my results or my model has high capacity of generalization. So I did that as a second phase of the research, I remember. So here is an example, for instance. This is a 5-fold cross-validation for the value of k. Here, for instance, each point corresponds to a single outcome, and the line, as you can see, goes through the mean, and the bars, which are from bottom to top, indicates the standard deviation. So according to this one, for instance, the k is, this is k, right? This is k. So the k, or the number of entities participating in this classification, around 7. If the number of k is around 7, then you see a better results, right? So this is one important thing that you should learn from this diagram. Okay, this is how you tune or fine tune your hyperparameters. K-nearest neighbor on image is never used. We have already mentioned this one. It's rarely used for deep learning, in deep learning, because it's resource intensive, so it takes much time to evaluate your model. And the other reason for that would be, it's not that informative. The first thing I said already, it's very slow, but the second one, it's not that informative. That means if you see this, for instance, this is the original image. This is a little bit perturbated image. As you can see here, there is boxed black squares, or black boxes here at the important features of the original image. Here we have a shifted one, for instance. Here we have tinted one, okay? But you could get the same type of L2 distance, which is Euclidean distance, uh, between or among this and all these images, even though their information is a little bit perturbated. So for that purpose, k-nearest neighbor might not be used most frequently in most image classification or any other general machine learning problems. Okay. So again, k-nearest neighbor is also prone to curse of dimensionality, as the dimensions in your input data or the problem domain gets larger, then the k-nearest neighbor cannot handle them. Okay, handle it. So let's summarize what k-nearest neighbor is. So we said in image classification, we start with training set of images and labels, and then we predict labels on the test set. Again, k-nearest neighbor classifiers predicts labels based on the nearest training example, which is a little bit the same as nearest neighbor, but the candidates for majority vote are larger than one in the case of k-nearest neighbor usually. The distance metric and the participants, that means k in the k-nearest neighbor, are called hyperparameters. So the recommended approach here is to choose hyperparameters using the validation set rather than test set and the training set. So, and finally, after choosing the hyperparameters based on the validation set, you can run the test set, or you can evaluate the hyperparameters on the test set once rather than multiple times, which is true in the case of IDEA 2, where the selection of hyperparameters is mainly based on the test set. So that being said about k-nearest neighbor, it's better to talk about linear classifiers. Look, this application, for instance, this some model, some random model, it could be any model. So we can say it's a linear classifier. Is classifying here these two human as two young girls are playing with Lego toy. For this one, for instance, a person is or a boy is doing backflip on wakeboard. The other one here, a man in black shirt, is playing guitar. These are basically classification problems and applications. And again, the corresponding model that performs this kind of applications could be, linear classifier or even non-linear classifier like neural network. So let's recall again CIFAR 10, which is a very popular data set in the realm of image classification and in general computer vision. So here, for instance, we see different sets of images under each category. Here you see we have 10 classes actually. We already mentioned about this one. So corresponding image for in each of these 10 classes is displayed here. as a sample. Just it's better to recall that it has 50,000 training images, and each image is 32 by 32 true color image. That means it's 3-channel image, and it has 10,000 test images. Okay, so when we talk about linear classifiers, we have to bring the concept of parametric classification or weight-based classification. So basically, we call this approach parametric approach. So we have here an image, and assume according to CFAR 10, for instance, it's 32 by 32 times 3 image. So totally it will have 3072 pixels, or basically pixels are defined in terms of pixel intensity, so numbers. So the parametric approach has this function f of xw, and this f of xw gives weight for each of the input images in terms of the already defined classes. Okay, so here, for instance, x is basically the image, the input image. Okay, w is the weight of each of these classes, okay, on this image. For instance, if you have like classes like A, B, and C, say there are 3 classes, possible classes, okay, then X is basically one image. So W is simply the weight assigned to assigned to this class, pertinent to or in relation to this input image. So basically, if you have 3 classes, then you will have 3 different weights for each of these classes corresponding to one image, one target image. Okay, so here, according to CFAR, there are 10 different classes, so we'll have 10 numbers. So the function this f of x w yields a list of 10 elements simply. So each value, each index in this list represents the corresponding weight of the classes in relation to this input data x. Okay. So there are different parametric approaches. There could be linear or non-linear. So here we are about to see the linear classification approach, linear classifier. So according to linear classifier, here f of xw is equal to wx. That means, as we already mentioned, f of xw yields a list of 10 numbers, but it takes the whole image, one image, okay, the whole pixels of one image, and the corresponding classes times corresponding weight of the image, okay, weight of the image. For instance, if you have 10 classes here and one image x, then the weight will be, for each of these x, you will have corresponding weight. Like if this image is, for instance, 372 pixels, 372 pixels, then each of these pixels, which is 372, will have 372 numbers weight corresponding to one class, and for all 10 classes we will have 372 times 10 numbers representing the corresponding weight of classes pertinent to this input image or input data. So I have been discussing about this one seconds ago. So here we have, for instance, f of xw, which yields list of 10 values, numbers, which is a one-dimensional list or array. Here we have f of xw is equal to wx. W is 10 times for each class, multiplied by the number of pixels of the input image, which is x. Okay. Again, we have x, which is the number of pixels representing that x. So here, for instance, the image is 32 by 32. So 32 by 32 times the channels 3 yields this one, 372. Okay, so basically x is 372 times 1. W is number of classes times the number of pixels in the image, and the function, the outcome of this whole function is a 10 by 1 array, which corresponds to the weight or the probability of each of those classes, or the probability of the image to be classified to each of those classes. Okay, to each of those classes. Okay. Um, yeah. The other approach in case of linear classifiers is the concept of bias. So usually we might not, or it might not suffice to only use the WX, that means weights with their corresponding image value. We might have to deviate the learning pattern by adding some bias value. Bias basically is a fixed constant value that affects the learning rate and curve of the learning model, linear classifier, for instance, in this case. So here, for instance, assume we have a 4-pixel image, which is 2 by 2 image, for instance, here. Then here, for instance, the approach that you follow while performing linear classification in our case, for instance, is that you have to transform this 2 by 2 matrix into a one-dimensional matrix, as you can see here, and then you have to multiply this one with the corresponding weights and come up with a for instance a linear, like a one-dimensional list that represents the classes, as you can see here. Okay, so here, for instance, in this case, just assume we got minus 96.8 for cat, the distance. Okay, here we have, this is bias, by the way. Okay, so here we have 437 for dog. We have 61.95 for sheep. So different scores you might get here from a linear classifier, and you have to choose the one with less distance, and assume just that label or that class is the one to be labeled to the input image. So we have already interpreted a linear classifier. We have discussed the correlation between this and this. We say this is the weight or the parameter. This is the corresponding image. This is an additional bias, which is by the way constant. Okay, so by simply multiplying the image, which is the image is not usually a 2D matrix. In this case, the image will be a 1D matrix. Okay, so by multiplying this image with its corresponding weight for each of those classes defined, okay, for each of those classes defined. In this case, for instance, we do have around 10 classes. So we come up with a result, which is if the number of classes is n, then n number of a one-dimensional list with n number of elements. Okay, so the index of the element, or the element with smallest amount of distance from the target element, or the input image, will be used and labeled as the class of the new image. So this at the bottom is how the f of x w, which is the wx plus b, yields this is a feature space basically. So for plane, for car, for bird, for cat, it generates this kind of maps, and from those maps, the one with similar or the smallest distance from the target image will be used, and the label of that corresponding image will be assigned to the new image. We have already discussed this one. So this diagram simply interprets a linear classifier, or depicts a linear classifier, and also the setbacks of linear classifier. So linear classifiers, you cannot define linear classifiers as, for instance, as like this. Linear classifiers cannot work like this, cannot categorize sparsed data into one group. That's not possible. Classifiers are more to this, straight lines. So when the data is very sparsed, when the nature of data is complex, linear classifiers might not be applicable. Okay, as you can see here, for instance, this is identifying or distinguishing this object from this object with straight line. So what if the sparsity of this data does not let the classifier to identify them or to distinguish them using such kind of linear lines or straight lines. So in such cases, which is a common case in machine learning or reinforcement, linear classifiers fall short. So there are different hard cases that you can mention, but let me mention one, for instance, which is a case of number of pixels which are greater than 0 and odd or even, for instance. So if you try to map numbers in a number array, for instance, let's say this is 0, okay? Here we have positive value, like 1, 2, 3, and the same is true for negative values, okay? Here we have -2. So in this graph, for instance, if you want to identify numbers which are greater than 0, sorry, and odd, and again, this is the first class one, okay? And numbers which are greater than 0 and even, which is class 2, linear classifiers cannot do this, because here we have, for instance, say for instance 2 is even, okay, 3 is odd, then we have 4 here, which is even. So you cannot get you know, a linear classifier that can classify like this, okay, even odd, like this. So such kind of situations cannot be addressed by linear classifiers, and for that we need some advanced classifiers like neural networks. Okay, we'll discuss about that one in the next classes. Especially deep learning based approaches are recommended in such kind of complex situations. But just to get to know how we started image classification, it's better to know about linear classifiers, specifically from the earliest stage, nearest neighbor, then k-nearest neighbor, contributed a lot. Then other linear classifiers are also parametric approach, are also or has also been have also been important. So it's better to know about them. So far we defined a linear classifier, parametric approach, which is a score function basically. This is a score function. You can call it a score function because it scores the input data against different classes. Okay, so the probability of one input data to be labeled into one of those classes is scored. Okay, so we can call it a linear score function. Okay, so the score might look like this one in the case of CFAR10, for instance. Okay, so how can we tell this W or weight is good or bad, for instance? That's one question for the next class. We mainly based on, you know, the loss functions, because loss functions contribute a lot for identifying something as good and bad. We might not discuss about loss functions in our formal lecture, but I hope, I mean, I believe you know about loss functions, different loss functions in your deep learning class, machine learning class, probabilistic graphical modeling class, and computational cognitive science class. But on the go, we might discuss some loss functions, which lets us know the goodness or badness of our weights. But we will not cover this chapter as a formal chapter. But I will send you, you know, the required documents from the Stanford visual recognition class, so that you read those loss functions by yourself, since it's out of the scope of this course. Thank you. So in this class, we have, as already mentioned here, we discussed about image classification, how hard it is, the challenge behind image classification, the earliest approach to classify images like nearest neighbor and k-nearest, and then we discussed about parametric approach, linear classifiers, linear score functions, and there we defined what each of the components of the linear classifier function or score function are, like what x is, what w is, the matrix structure of x and w, how we can compute x with w as wx. We discussed about the conversion from a multi-dimensional matrix of an image x to one-dimensional matrix, so that we can multiply it with or compute it with the corresponding weights for each possible class of x. Then we also discussed about the need for bias, the benefits of using bias while building a linear classification model. So that's all for this class. Next, we'll discuss about deep learning based classification algorithms. But before that, I will send you a lot of reading materials that will fill the gap that we have, because we are not covering, some basic concepts regarding machine learning, because our main purpose here is not to learn about machine learning. We assume you know machine learning because you took machine learning courses, deep learning courses. So for that purpose, I will give much emphasis for machine learning for computer vision and deep learning for computer vision aspects rather than the nitty-gritties of machine learning and deep learning. So for that purpose, in case if you didn't read enough in your previous courses, then I will send you some reading materials so that you can read them and um, catch up with this course. So that's all. Thank you. See you again on the next class.